Hi all. In this video, we see thesis written by Gerard from Connemara University about the title "Automatic Steering Method for Autonomous Automobile Part Tracking." So this thesis is about different kinds of part tracking algorithms written for automatically steering the car-like robots. So this thesis is written during the year 2009, but still valid even in this 2025. So this thesis is about something like comparing different part tracking methods which were promising applied in Darba Grand Challenge and Darba Urban Challenge for controlling a car-like robot along a predetermined path. So there are different kinds of path tracking models, but this thesis have selectively taken models which are very important for path tracking and which are very ease of implementations and tuning and have high computational efficiency. So the author acknowledges Dr. Chris Thompson and his advisor Reed Whitaker, and they have used CarSim and different uh, tools for testing these path tracking methods. So these are the different chapters, and we would be mainly focusing on uh, chapter 2. So this introduction, they says that there are many research has been put on developing autonomous car-like robots, and most of these autonomous car-like robots are developed using a simple and naive controlling strategies and system models for vehicle controls, and that too has become a very successful in bringing the autonomous vehicle projects like Sandstorm, Stanley, and Boss from Connie Mellon. So these were tested or applied during Darba Grand Challenge and Urban Challenge. For example, Sandstorm use a simple steering controller based on geometry vehicle model. Stanley, a vehicle from Stanford University, during the Grand Challenge use a simple kinematic vehicle model called a Stanley method. And Boss, obviously, they used a model predictive control strategies to perform vehicle control. But although they used high computational expensive model predictive control, the mathematical models used were very simple kinematic model of the vehicle included in the optimization of the steering controls. So why does this simple methods have been successfully utilized and not very complexity models? But to be honest, this doesn't stops the people from doing an extensive research in this area. But despite that, there are these following questions arises: why these simple methods commonly used in practice? What about this existing theoretical research going on? And what are the other good matches between these applications and the methods identified? What are those limitations of these promising simplistic models? And what would be the future breakthrough? So these were the questions raised during this thesis, and for this there are different classes of controllers have been put into comparisons in this thesis, and they are commonly called as vehicle controllers or part trackers. And some of them, these things are based on a geometrical methods, which you will be seeing foregoing. This will be seeing in this video. And one of the main all of these part controllers or vehicle controller is to minimize the lateral distance between the vehicle and the defined path, and also to minimize the difference in the vehicle heading and the defined parts heading. But despite using this part trackers, the objective is to use methods which are very less complexity, and these geometrical based methods that we will be seeing in this video exploit some geometrical relations between the vehicle and the part to design the control laws. and these have certain limitation that also we will be commenting on this video. And chapter 3 is about how to use an optimal control law based on constrained optimization problems. And chapter 5 also will be focusing on a constraint optimization control problem like called as model predictive control. So these methods are being tested on a car simulator on different tracks like lane change course, something like this, and also 8 course, something like the track is defined in the blue curve, something like what is defined in the figure 6. And finally it will be like a race course where have a different curvature and different speed maneuvering, and those are the blue curves that are aimed to be tracked for different velocity fields. Now let us see two important path tracking methods which were very successfully applied on many car-like robotic controllers. So these are geometric based method. The meaning for geometric based method is like they try to utilize geometrical relationship between the vehicle and the path tracking and the path resulting in control law. So the important concept is to use a concept called look ahead distance and to measure the error ahead of the vehicle, and can extend to do some calculations based on some geometrical relationship between the vehicles and the path that has to be tracked. So the first path tracking method based on geometry vehicle model is a pure pursuit. So this is a geometrical model that a vehicle is trying to go along a circular arc, and this is the radius of curvature, and this is the wheelbase L, and how this is something like how much angle it deviates from the um how much angle that has to be tuned for the to follow the circular arc for the front wheel steering. So we utilize a bicycle model. Bicycle model is nothing but a four-wheel model as a two-wheel model, and that can be only move on a plane. So based on this geometrical relationship, then how much that has to be steered to maneuver along this circular path is defined by this relationship L by R. Tan delta is equal to L by R. And L is as already mentioned is a wheelbase, and R is the radius of the circle. And the pure pursuit the same geometrical relation applied a bit that the aim of this pure pursuit method is the first step is to along this path we make a circular arc, and the circular arc intersects the path at the look ahead distance, and the point is known as gx by gy. We define a look ahead distance to make this circular arc to intersect at this path, and the aim based on this geometrical relationship we deduce a relationship based on the trigonometrical laws like LD by LD is a wheelbase and R is a radius of curvatures. So we use a trigonometric relation to sine 2 alpha is equal to 2 sine alpha by cos alpha, and sine pi by 2 minus is equal to cos alpha. This cos alpha is cancelled here, and finally we get this relationship here. Then the alpha is something defined here is the difference between the vehicle's heading vector and the look ahead vector. So this is the rear wheel point, and this is the look ahead point. This straight line gives you an angle with respect to the coordinate systems, and this angle and the angle of this vehicle, the wheelbase angle is given by this alpha. This difference in this look ahead angle and the orientation of the vehicle is the alpha, defined as an alpha, or called as a heading error. And finally the sign of this heading sign of this r is replaced by 1 by r is the radius of the curvature of this arc, and this gives you this relationship. And previously we have mentioned that geometrical relationship like tan delta is equal to L by R. So using this relationship we can, and that obtained relationship we get the final what angle we have to steer to maneuver along that path based on the look ahead distance to reach that point. Like look ahead point gx by gy is given by this tan inverse of 2l sine alpha by ld. So this can be also seen in a different way using the sine alpha is equal to 2ld by k, and that that is like e is something a lateral distance between the uh, vehicle and the geometrical path. So this is one other way to look ahead how this relationship exists, and it not necessary to good focus, but this is the main steering angle calculation based on the pure pursuit assassin. So what does this pure pursuit do is we have a path, a curvature path that has to be tracked properly. So it does make a look ahead distance of certain length, and that look ahead distance take you to a point called gx by gy, and that orientation, that curvature and that path orientation and this orientation of the vehicle gives you an angle alpha, and this is wheelbase, and based on this input you can get what steering angle has to be maintained so that it doesn't move away from the curvature of the path. So this looker distance not necessarily be fixed. It can be a function of the velocity. A more higher velocity will give you should go for a longer looker distance, and lower velocity should go for a shorter looker distance. But there should be a as minimum and maximum value which has not to be exceeded in the either side. So the here they set to be minimum look ahead distance to be 3 meter, because for zero velocity it goes for a high value, so that should not happen. So so it should be a 3 meter, and maximum would be a 25 meter value. So putting this things into the simulator for different things, they observed that pure pursuit seems to be a very stable and robust method, uh, and it seems to be like very less oscillatory, and looker distance provides more accurate tracking, while longer distance provide short looker distance provides more accuracy, as we can have a short sharper turn, but longer looker distance don't gives you an instability problem, but it gives you a smooth tracking. So decreasing the value gives an accuracy but causes instability, but a value of large value may be a poor tracking, but it's a very stable and a smooth tracking. So this is a hyperparameter that has to be play around based on the path curvatures. But one of the insufficient thing is that it results in cutting corners, and difficult to balance with the peer pursuit for either to have a trade-off between the performance and the stability. The reason is the peer pursuit is based on geometrical method where it highly ignores the curvature of the path. But one advantage is it's a very high level of robustness to make a quick transition to be applied in any test, and fairly it can also give a good robustness during the high speed test. So this is the same thing that depends upon the way small value or a large value. How does that affects either the stability or the accuracy? So the final comment would be that decreasing the look ahead distance results in a higher positions, but results in a stability problem like more oscillations. But increasing the look ahead results in a promising smoother way, but eventually it has a poor precision tracking when it is going to be have a sharper curvature path. The second method is again a geometrical based method called the Stanley method, which was successfully applied in by Stanford University team during Darba Grand Challenge and Urban Challenge. And this is the path to be tracked, and the vehicle is offset of EFA from the track. and the heading error also seems to be like difference between this heading orientation of the vehicle and the path of the vehicle is gives you the steering angle. So it has two terms. Only the first term is the obviously the heading error difference between the orientation of the path and the orientation of the vehicle, and the second term is somewhat a nonlinear term, which we may have a future see about how this Stanley method is derived. And this is a nonlinear term which is proportional to the lateral offset distance between the vehicle and the path. As EFA increases, we have will we this path this gives more steering angle to uh, keep track along the path, and k is a gaining factor which will be based upon the velocity. Again, as k is increased here, tracking performance increases. There would be an upper limit to guarantee a stability. The more k, the more sharper and more becomes yeah, oscillations or instability. To be here, they have mentioned that they are not as robust as pure pursuit in lane changing. But one of the advantage of this Stanley method is has uh, despite it has some trouble in discontinuity and using in the discontinuity of the path like lane change, it has more works well under normal condition, especially at a high speed. So this method is more suitable for a high speed driving in comparison to the pure pursuit. So these are the two methods which were promising things, even despite they are very much old. They are very much utilized in even in the present world of 2025. And later we will see about the chapter 3 of optimal control based path tracking methods like LQR or model predictive control in possibly in the next video. Yeah, thank you.